Hey everyone, welcome to the Project 4 walkthrough video. This video is going to be shorter than last week's video because I thought that was a little long. Now, Project 4 is going to have you implement locks and condition variables that build off of the threads that you implemented for Project 2. In Project 3, you already learned how mutexes and condition variables worked as the client. So now you'll actually go into them and see how to implement them. I personally thought Project 4 was much easier than Project 2. So hopefully you'll have the same experience when you implement this project. All right, so another thing that's interesting about implementing lock and condition variables is that this basic mutex and condition variable you're going to build is going to form the basis of what you will implement in CS 112, where you'll implement more complicated mutexes and condition variables. So yeah, I feel like this is a good preview of what 112 looks like. And 112 is a great class. Highly recommend it as a follow-up to 111. Okay, so let's just quickly go over how Project 4 relates to Project 2. So if you go to the starter code, let's find the starter code. So there is no new starter code. What you do is you make a copy of your CS 111 Project 2 starter code. Let's call it CS. So let's make a copy of it. And then here you can see that in thread.cc, you should have already implemented this from Project 2. Now, if you got your Project 2 grade back and you had some bugs in it, then I highly recommend that you go in and you fix those bugs. In my experience, when I implemented this, I don't think most issues in Project 2, like most edge case issues, won't impact your Project 4 tests, but just to be safe, I still recommend that you fix everything that the grader commented on before you move on to Project 4. Okay, yeah, because debugging both projects at the same time is pretty difficult. Now, everything you'll be implementing in Project 4 is going to be in sync.cc. So this is the implementation file for the code for the mutex and for the condition variables. So here's the three functions for the mutex. Here's the three member functions for the condition variable. The declaration, the header file, there is no sync.h file here, but it's given at the end of the thread.hh file. So you can see here that there is a mutex declared here, and there is a condition variable here as well. So yeah, you might need to add some of your own private members for both the mutex and for the condition variable. Okay, and these are the only two threads you need, not two threads, two files that you need to edit, thread.hh and sync.cc. Now, the test harness, as you can see here, the test harness, there's a test harness here. The test harness, you'll remember these tests from the thread, the Project 2, right? I hope you are intimately familiar with how these tests work. I'm sure a lot of you spent a lot of time debugging this. So the test for the mutex and for the condition variable follow that. They're down here. And these tests, you can see that they're pretty similar to what the previous test was. Instead, now we create a condition variable or a mutex, and then you use your Project 2 code to generate some multi-threaded program, right? Like here, we call the create function that creates a thread that runs this lambda function. Inside it calls lock and unlock on that mutex. And then, the yield calls here. It's very similar to the Project 2 test cases, but instead we just add a mutex and condition variable to confirm that those two synchronization primitives work in a multi-threaded program. The one thing you should be aware of is that these test cases don't use preemption at all, right? You remember the last step in your Project 2 was to implement preemption. And then that allowed the scheduler to preemptively stop a thread to switch off to another thread, right? But all the test cases here will not use preemption at all. It's just more difficult to test. So yeah, when you are trying to trace through this code, you know that a thread won't get switched off until it calls yield. Okay, it won't get switched off until it calls yield, or when it calls some functions like lock, where it might get switched off later. More on that later. All right, so that's mostly it for the test cases. We might come back to this later, but I do want to talk about the code that you're going to write here. So let's talk about the mutex. Okay. Now, what I recommend that you do is that you should go back to the lectures that talk about the locks and condition variables. So here during week 2, you covered what locks and condition variables were. I'm sure a lot of you spent some time reading that when you did project 3. Then there's this lecture called implementing locks, which goes over how to implement a mutex. Okay. And the nice thing about the mutex is that John during lecture basically gives you the solution for how to implement a mutex. Right. This is technically not like, well, I mean, it's pretty close to C++ code if you ask me, but yeah, this is essentially the pseudocode for what your lock and your unlock functions should do. Okay, so let's just quickly take a look at this. Now, in lecture, you covered both the uniprocessor and the solution for a mutex and a solution for multiprocessors for when you have multiple cores that are, and you need to lock a mutex that is shared among multiple cores. Now, for the midterm, you definitely need to know this multi-core machine locks, but just for this assignment, you only have to worry about the single processor. So you don't have to worry about spin locks, you don't have to worry about atomic exchanges. You'll just have to implement this uniprocessor solution. Okay, so before we jump into the pseudocode, let's just briefly review what these threads are and what the synchronization, or not synchronization, but what the scheduler is doing when you to these threads. Okay, so here I'm switching to the iPad. Okay, I've switched to the iPad. So let's talk about what happens when to a thread. So first you create a thread, right? We call create. We call create, which creates a thread. Okay, so then it's a new thread, it gets put in in some new state. And then once you create that thread, remember at the end of that constructor, right, you called schedule. And schedule is the one that puts it into the ready queue. So now it's in a state what we call ready. Okay, so basically this means in ready queue. Okay, any thread in the ready queue is ready to run. So the scheduler can then go in and pick out a thread from the ready queue to be running. Okay, so switch on. Okay, and this running thread is the thread that you get when you call current. Right, thread : current. Okay, now how is it switched on? Well, in project 2, you implemented this switch function, right? The switch function takes some thread that is in the ready state and switches it so that it's now in the running state, while it also takes the running thread and it switches it off. Okay, now when you switch the thread off, it doesn't go back to the ready queue, right? You have to separately call schedule so that it goes back to the ready queue. So this switching off, this part is what we call yield, right? Which, if you remember from project 2, this was a combination of schedule plus switch off. Okay, and then you also had a function called exit, which will exit the currently running function. So that would be call exit, and then your thread becomes finished. Okay, there's a little more to being finished, right? There's a whole destructor thing, but we'll not worry about that. This is a main idea of what the flow chart of your threads are going through, right? They get created, scheduled, and then they get switched on and off. Okay. Yeah, there is another way a thread can get switched off, and that is if it's preempted. Okay, but yeah, for this project, for project 4, we won't worry about that. Okay, you did implement that for project 2. Now, what we're going to think about is there any other states that your thread could be in? And it's possible, right? Your thread, imagine your thread tries to acquire a lock, but that lock was already locked by some other thread. So your thread now needs to wait until the other thread has released that lock. Okay, so what happens in that case? In that case, your thread should no longer be on the ready queue. Any thread on the ready queue is eligible to be run, but your thread that is waiting for the other thread to finish until unlock, that thread can't run. So that thread cannot be on the ready queue. That thread is going to be in a state what we call the blocked state. Okay, and how does a thread become on the blocked state? Well, a thread becomes on the blocked state when in project 4, it happens when the mutex tries to lock already locked. Okay, that's one way it could happen. The second way is for condition variables when you call wait. When you call wait, that thread goes to sleep, it becomes blocked. It's not on the ready queue. It cannot be scheduled. Scheduling is putting it on the ready queue. It cannot be switched on and starts running. That cannot happen. Okay, when it sleeps, it becomes blocked. Condition. Okay, there are other ways for a thread to be blocked. For example, if it's waiting for file IO, or if you call sleep explicitly. But for this project, these are the two you have to worry about. Now, when a thread is blocked, where does that thread go, right? It's not in the ready queue, and it's not in the current. It's not like the current thread. I know that most of you have stored a current pointer as a static variable. Right? It's neither of those. Instead, when a thread is blocked, what should happen is that you need to store this thread somewhere. Okay, and where does it make sense to store the thread in? Well, if it's waiting on a mutex or on a condition variable, you want the mutex to be able to find, once the mutex is unlocked, the mutex needs to know which thread should be able to get the mutex now. Okay, that is a thread that should get unblocked. So the mutex needs to sort of store these threads that are waiting on it in some sort of data structure. Okay, and for this project, we'll be doing we're going to assume that the mutex and the condition variables, they will choose who gets to acquire the lock next based on a queue. Okay, so FIFO based on the queue. So this will be on some queue in mutex or condition variable. Okay, if it's on that queue, each lock has its own queue. Each condition variable has its own queue of who is waiting for it. Okay, and then when a thread is ready to be unblocked, the mutex then looks in and picks out a thread and then unblocks it. Okay, and when it gets unblocked, now this is important. When the thread gets unblocked, it then moves to the ready queue. The mutex is not responsible for running the thread immediately. Right, that's your dispatcher, that's your dispatcher's job, right? You are not going to immediately start running it. Instead, when you unblock a thread, you are saying, okay, this thread is ready to be run, and you put it back onto the ready queue. Okay, do you remember which function in your project 2 puts a thread back onto the ready queue? Yeah, it's schedule. Okay, and this happens when you either, for the mutex, other thread unlocks, or 2, for a condition variable, other thread calls notify, either notify 1 or notify all. Okay, yeah, when that happens, the thread unblocks, it wakes up. That's what we mean when we say wake up. It means it gets put back onto the ready queue and it's ready to be run again. Okay, important, the blocked, you don't move from the blocked state directly into the running state, right? There is a thread that's running right now. You can't just skip the line and have it immediately start running. All right, so this is like a grand picture of how you want to implement the project 4 code. Okay, everything in green is what your project 4 is going to add on top of everything in white that was implemented in project 2. Now, I wanted to add one more thing. I think, yeah, I didn't write what you need to call for this arrow for how do you block a thread. While blocking a thread, think about which function in your code blocks a thread, right? Here, when we go from the running thread is the thread that is currently on, you'd want to switch this thread off, right? You'd want to switch it off. Okay, you don't want to switch the thread off. So kind of like this part, but you don't schedule the thread, right? Because scheduling that thread would put it onto the ready queue. Okay. Instead, what queue do you want to put it onto? You want to put it onto a queue that is the queue that's waiting for the mutex or for the condition variable. Right. So I hope this is helpful. This is like a grand overview of how these threads, like what's happening to these threads as you call your different functions. So now let's actually go into how you implement a mutex. Now, John gave you the pseudocode, so let's walk through the pseudocode. You have a constructor. The constructor doesn't do anything except just initialize the variables. Your member variables, you have an integer locked. This is just like a Boolean. That's whether or not this thread is currently locked. You also have a thread queue, and this is that queue I was talking about, right? It's a queue that's storing all the threads that are blocked and are waiting for this particular lock. Important, this thread queue is not a static variable, right? It is a member variable. It's not static. A static variable would be a variable that's shared among all locks, but each lock has different threads waiting for it, right? One thread is going to be waiting for a single lock. It's not going to be waiting on multiple locks at once. So each lock should have its own thread queue. Okay. In fact, I don't think any of the member variables for product 4 should be static, okay, because you're implementing for one particular lock or one particular condition variable. Okay, so let's look at the code. Here you'll see that our friend enter disable and enter enable are back. But remember, you should never call those functions directly. Instead, you should use interguard, right? We hinted at this for product 2. I know that during the grading, some students are still not using interguard. You have to use interguard here. It's super important for this project because this project adds exceptions. And what happens in exceptions is you jump out of a function and then you accidentally skip the enter enable at the very end. Okay, so the whole point of interguard is when that interguard goes out of scope, no matter how you go out of scope, whether you finish the function or you jump out of the function, the enter enable gets called. Okay, it's called RAII. I went over that last week. This week you must use interguard. Same down here. Okay, and why do we disable interrupts again? It's because multiple threads might try to call lock at the same time, and you don't want multiple threads to be in this critical region, right? You have a thread queue that's shared among multiple threads. So if you try to modify this queue simultaneously from multiple threads, you might end up in some inconsistent state. So make sure you turn off interrupts using interguard. All right, let's look at the code for lock. So when you call lock, you first check if the lock is locked. Right? If it's not locked, if no one else has acquired it, then you can acquire it, no problem. And you're done, right? You've acquired the lock, you've set it to locked equals 1. So everyone else knows that it's locked, and you can just continue doing your own work. However, if it is locked already, then you can't lock it. Someone else has locked it. You can't lock it anymore. So this goes back to that diagram I drew where now you will be blocked, right? That's why you call it a block thread here. And before you block, you have to add yourself to the queue of people that are, or not people, threads that are waiting for this lock. Okay, it's a queue, you add yourself to that queue. Now, so that is the lock function. So if you call block thread, you should end up being blocked. You should be going to sleep. Now, just a question, is block thread, is this yield? No, this is not yield, right? Because what yield does is yield will schedule the thread and also switch the thread off from so it's no longer running, right? But it should not schedule, because schedule implies that it's adding it to the ready queue, right? If you actually look at that diagram that I drew earlier, right? Yield lets the thread go from running state to ready state, but you want it to go from the running state to the blocked state. Okay, so we don't want to schedule, we just want to switch that thread off. All right, for unlock, it's pretty similar, except now imagine that you are unlocking the thread, and if no one else is waiting, then cool, you just set locked to 0. So other threads, if they try to lock now, they're able to just acquire the lock without waiting. If there is a thread that is waiting, however, okay, they'll be in the queue. So you can pop someone from the queue. Okay, because we're doing FIFO, that person you pop from the queue, that's the one that has been waiting the longest, and they should get to run next. And what you want to do, what this thread needs to do is it needs to take that thread and turn it so that it's no longer blocked. Now it is ready to run. Okay, then how do you move a thread from the blocked state to the ready state? Right, remember, ready state, all threads that are in the ready state are in the ready queue, so you have to add it to the ready queue. Okay, think about which project 2 function does that. Okay, yeah, and that is a quick overview of the lock function. A couple other hints I want to tell you. Yeah, so in the API for locks, right, this lock and unlock, yeah, this basically explains what I just went through. There's this extra function called mine, which returns true if the calling thread owns the lock and false otherwise. And you might look at this and think, well, how do you, if you look at the pseudocode, you might think, how do you know what thread owns it, right? If you look at the lock, you just have an int variable that's storing whether or not a thread is locked, but you don't necessarily know who has locked it. Okay, luckily in the section handout, Jerry actually gives you a hint. So let me just point out the hint from the section 4 handout. Here it says the mutex class keeps track of the thread that owns it. So your mutex class needs to somehow keep track of the thread that currently owns the lock, has acquired the lock. Okay, so yeah, you probably want to add some other thread variable here that is remembering who has locked it. Every time you call lock, remember just to change who that variable so that you know that this is the thread that's locked it. And when you unlock it, be sure to change it back so that you're no longer the one who has locked it. That way, implementing mine is easy, right? You can just check if that variable, the variable that stores what thread has locked a lock, is the same as your the current thread that's running. Okay. Let me just go through my list of hints. Yeah. So remember, we're doing FIFO ordering. That's why we're doing the queue here. Block and unblock. I went over this in the flow chart. Don't get confused about when. Don't get confused about here. Make sure you're not calling yield, right? Yield will put the thread back onto the ready queue, but it should not go on the ready queue. Okay, so yeah, remember the differences between each of the functions in project 2 and make sure you're calling the right one. Next, remember, you should never start running a thread immediately, right? A thread does not go from the blocked state to immediately start running. Okay, there's some cases maybe outside of this project, but for this project, a thread, when you get unblocked, should not directly start running. Instead, it should be put into the ready queue. Okay, and just check which function you wrote from project 2 implements that. Lastly, just wanted to remind you all that you're definitely going to call a lot of functions in the thread class, right? I mean, I just went through and hinted that you should not call yield, but you might want to call something else, right? So make sure you check those functions out. And when I say add something to the ready queue, you don't want to go into the thread class, take the ready queue out, and then manipulate the ready queue yourself, right? Because that would be sort of breaking the abstraction, right? Why is a mutex? Why is your lock, who is it's a client of the thread class? Why is it going into the thread class and manipulating its internal variables? Instead, you should be calling the public functions of the thread class, whether the public member functions or the static functions. So you should be calling yield or schedule or switch or exit or create. You should not be taking the ready queue, manipulating it, or taking the current running thread and manipulating it. Okay, always go through those public functions. All right, let's go through the starter code. And just wanted to point out a few minor things. Also, I realized I'm almost out of battery. Let me pause the recording. How do I pause the recording here? Pause recording. All right, welcome back. So now we are charging. You can see up here, I'm charging. So won't run out of battery. Yay. All right, let's look at the starter code. So first, let's look at the .h file. You'll see that we've already declared the 3 functions you have to write for you, so you don't have to modify any of those. They're member functions. Okay, so no more of the weird static functions. These functions all are modifying a single mutex. Now you'll notice these 3 look kind of weird. So let me just briefly explain these. This is the constructor. right? Like before, but you have this equals default. So what that means is it's saying, I want to default initialize all of the public, all of the, not public, all of the member variables. Okay, so for example, if you had like a vector here, let's say you had a vector here, then what default means is the constructor will default initialize this vector. Okay, the default constructor for vector is just an empty vector. Okay, now the weird thing about default initializations is that it doesn't treat like primitives correctly. So for example, int, if I had like a variable x here, so I'm not sure about x. I believe it won't initialize this correctly. Okay, so this might still be some garbage value. And if you do something like red star t, right, a pointer, then it won't initialize this correctly either, right? It's not going to be default initialized to null pointer. So don't assume that for primitive types, it's going to default initialize it to the right thing. Okay, for objects, it will just call the constructor. You'll be fine. If you declare a, what other objects have we done? Okay, no, I don't want to declare a condition variable. If you declare other things in here, then they will call the default constructor. But for primitive types, not necessarily. Okay, and this becomes like an issue because sometimes like I personally got stuck on this for an hour. I assumed that it would get default initialized to null pointer, but that's not the case. Okay, it's just going to be some garbage value. So instead, what you need to do is you have to initialize it yourself. Okay, so for example, you can initialize it like this, so that after the constructor is called, you are guaranteed that t will start off as null pointer. Okay, so just make sure you do, for the primitive types, do a thread something equals that, so that when you are implementing it, when you are in your later functions, you can assume that when the mutex gets created, it's the initial value is going to be null pointer. Okay, so just a reminder, make sure you do that. Okay, what is next? Next, I want to talk about these two. Right now, these two are not as important for your code. Like you won't really need to implement them, but if you try to modifying the test harness, or if you try to write some code using your mutex, you might run into issues with these. So let me explain what they are. This one is called the copy constructor. And this one is called the copy assignment. The copy constructor gets called when you create a mutex that is a copy of another mutex. So let's pretend we're doing a vector. Okay. If we're going to create a vector as a copy of another vector, then vec is a copy of another vector. And here, because we're constructing a vec, so because we're constructing vec, we're calling the copy constructor here. Okay, it just copies another vec to vec. The copy assignment, on the other hand, is if vec already exists. So here, vec already exists, and then we're going to assign it to some third vec. So now vec is a copy, third vec, third copy, or third vec. Okay, so then this vec then becomes a copy of third vec. Okay, so that's what these two functions are. These two are the copy constructor and the copy assignment. All classes in C++ have these. Okay, sometimes you just don't, like you did not implement one for the thread class. If you don't implement one, what happens is C++ provides a default one for you. So that's what this means. This is just explicitly saying, I want the default one. Okay, the default one just copies all the members. Okay, now in this case, in mutex, we specifically say we want to delete it. Delete means do not let anyone use this function. Okay, so for mutex, you are not allowed to do this. Okay, this is forbidden. Okay, and then you can think about why, right? If a mutex makes a copy, what exactly is that copy? Right, that doesn't really make sense, because then is your thread trying to lock the original one or the copy? When you call unlock, does it affect the copy or the original one? Right, that just doesn't make sense. Mutexes are dangerous to be copied, which is why C++ forbids them. You should have already run into this issue in Project 3 if you try to copy a mutex. Okay, yeah, there are ways around it, like declaring references, which we'll actually talk about below. Okay, below you'll see that a private member here is a reference to a mutex because you can't copy the mutex. Okay, so similarly, the copy assignment also gets deleted. Okay, now you don't have to do anything special. You don't have to implement anything special. Just wanted to point it out if you get an error message about copy assignment or copy deleted or copy constructor. Yeah, in fact, you probably should have seen like this syntax from your error messages, right? When you used the standard libraries Mutex. All right, that's it for the Mutex class. Let's talk about the condition variable. Oh, actually, before we go to the condition variable, just last thing about the locks, the mutexes, you'll see that there are now exceptions here, right? You can just ignore this line and write your code below that. So your interguard, for example, you'd want to add it here. Okay. Yeah, technically, mine also needs to acquire to disable interrupts. So you'll do like an interguard here as well. So yeah, you don't have to worry about interguarding this part because mine will get the interguard. But this is also why interguards are important. You can't just manually enable and disable because you're throwing an exception. And if you do it incorrectly, you will forget to enable. So make sure you use interguards here. Okay, let's talk about condition variables. So the condition variable, it was covered in lecture, like what condition variables are, but John did not tell you how to implement condition variables. So something you'd have to think about yourself, right? But it's very similar to how we implemented a lock. Right? You still have threads that are waiting on the condition variable, right? But instead of just waiting so that someone else unlocks it, you're now waiting until another thread calls notify. Instead of calling it notify one and notify all, here we call it signal and broadcast. They're basically the exact same thing. Signal is the same as notify one, and broadcast is the same as notify all. So yeah, they behave the exact same way. It's just in OS and in C in particular, we like to name it signal and broadcast. All right, now let's think about what wait should do. All right, so if you go to the condition variable lecture, even though you're not given a pseudocode of what wait is doing, the explanations sort of tell you what wait does, right? What wait does is wait should atomically release a lock, put the thread to sleep until you're notified, and then you wake up again. Then you reacquire the lock before returning. Okay, so those three steps are the three steps that you need to perform in your wait function. Okay, now what's important is that the wait function, before you call wait, you should have already locked a condition variable, right? Yeah, I mean, you all did that in project 3, hopefully. So here you release that lock, put thread to sleep, and then when you get woken up, reacquire the lock. All right, now, the question is, you know how to do the first step and the third step. The question is, how do you do that second step? Now, we're not telling you explicitly like the pseudocode for it, but it's fairly similar to what we did for the mutex, right? The mutex had a queue of threads that are waiting for the lock. Here, you're not waiting for the, well, you are waiting for the condition variable, right? You have a list of threads that are just, you need to remember these threads, which threads are waiting for the condition variable. Because later, when you call signal or broadcast, signal, you need to know which thread to wake up, right? And then the thread to wake up is the one that has been waiting the longest. In our implementation in project 4, we want the thread that has blocked the longest. Okay, so the FIFO order still works. Recommend that you use a queue. The one at the very front is the one that has waited the longest. So you want to wake that thread up. So yeah, your condition variable needs to keep some data structure, probably a queue of all the threads that are waiting on it, so that whenever you call signal or broadcast, you can just go through that queue and wake up one of them. Now, remember, what does waking up mean? Think back to that flow chart, right? Putting a thread to sleep is not yield, because yield puts it onto the ready queue, right? It puts on the ready queue, then it becomes ready to run. No, this thread is not ready to run. It's waiting until someone else calls signal. So putting a thread to sleep is not the same as yielding. It should not go back onto the ready queue. Instead, it should be put into this queue for the condition variable. For notify one, waking a thread up is not the same as putting it as the running thread. Okay, you never changed what the running thread is. In fact, the thread that's calling signal, that's the running thread. Instead, when you call notify one, you should be putting the thread back onto the ready queue, right? So that it's ready to run. It's woken up and it's ready to run. Okay? And notify all is like, it's kind of like notify one, except you want to do it for every thread, not just the first thread in the queue. Yeah, so I think that is it. Yeah, there's this note over here. After notify, the waiting thread goes onto the queue waiting for the lock. Yeah, so I said it goes onto to the ready queue directly. That's not actually true, because remember, you are actually holding the lock, right? After notify, the waiting thread goes waits for the lock. Yeah, because later that the thread will, if you put the thread onto the ready queue, right, then that thread will then, even if it gets scheduled later, the thread that is notifying is actually owning the lock. Okay, so that thread that just woke up, even if it gets to run, it won't run immediately because the notifying thread still owns the lock. So, then this thread gets put onto the queue for the other one. Yeah, this is just like an explanation of like what happens if in this case. But yeah, I don't think you have to worry about actually implementing this. But it's important for important for the midterm, right? Think about if a thread wakes up, it gets put onto the ready queue. Then when it reaches the front of the ready queue, if your notifying thread is still running and it still owns the lock, then this thread that got woken up will be put back to sleep. And this time it's waiting on the lock, not on the condition variable. Okay, but once the notifying thread releases the lock, okay, then it goes back to the lock part. It gets to the front of the queue for the lock, and that's where it's able to actually start running. Okay, again, this note is not important for this project really. I think you can just focus on the others, but for the midterm, I recommend that you focus on think about what this means. Okay, so that's it for condition variables. Let's look at the starter code. Let me think, check are there any notes I have to give you for condition variables. Yeah, there's a minor difference between our condition variable and the condition variable that you used in project 3. In project 3, the wait function would take in a lock, right? That's the lock that you have already required before you called wait. You would release the lock, sleep, and then reacquire the lock. Now, on a single condition variable, you're pretty much always going to be locking and unlocking the same lock. So instead of, yeah, so that's actually this error here, right? You always wait on the same mutex, and it's an error if you don't always supply the same mutex. Okay, so to simplify error checking, because we don't want you to have to do a lot of if else checking if the mutex is the right one. Here, what we're going to do is we're going to just initialize the condition variable with the mutex. And it is implicit that every time you call wait, you're passing in this mutex. Okay, just implicitly, it's stored as a member. Okay, otherwise, all these operations is the same. You can just pretend that this was passed as a parameter. Okay, now, there is a small thing you have to be careful of here, which is this is a reference. There's nothing you have to do differently. Okay, yeah, in fact, the starter code handles it for you. So you don't have to do anything differently about this mutex. But just wanted to point out that it's a mutex. It's a reference to a mutex because you can't copy the mutex. Okay, so you pass in a mutex, but you can't copy it. So instead, you store a reference to it so that any change you make to m underscore impacts the mutex that you passed in by reference. This is an interesting case where the initializer list, the member initializer list, is mandatory. This code would not work if you changed this to m underscore equals m. And the reason is because this uses assignment, right? M underscore is already created, and now you're reassigning m underscore. And the thing is, references are aliases to other variables. They're just another name for another variable. So m underscore here is another name to m. And aliases, the references cannot be reassigned. So once you construct it, you can't reassign. That's why a member initializer list is required. This is saying construct a reference using m, rather than construct a reference by default and then reassign the reference. You can't reassign references. Okay, yeah, but otherwise, yeah, you don't have to worry about this. This is just a fun C++ stack. You don't have to change m underscore at all. Okay, it's declared for you. You just use it. Do I want to explain explicit? now we're getting to C++ trivia. I don't know if anyone's going to ask what explicit is. What explicit means is explicit means you can't just, so I don't know. I don't even know if I want to explain this. If you don't have the explicit, then this code would technically compile. Declare a mutex, condition C is equal to 10. Yeah, okay, so in C++, these two lines of code are very similar. These two lines of code are very similar. Okay, these are both calling the constructor for condition by passing in the mutex. Okay, but this is like explicitly saying call the constructor using this. Well, this is something that we call, I think it's a copy initialization. And like this looks weird, right? This just doesn't make any sense because these are different types. So explicit is a way to prevent you from creating a condition variable using this syntax. Okay, you have to use this syntax, which makes sense, right? The standard vector also has the same explicit. If you look at the constructor for vector, it also has that. So if you try to create like an empty vector of 3 elements, right, that is different than, you can do that, but you can't do this. This is forbidden. Okay, so that's what the explicit keyword is. Again, not important for the project, but just in case anyone asks what this word is, I'm just there to explain it. Cool. There's nothing interesting with the starter code. It looks exactly the same as the other ones. Okay, and I gave you a hint as to how to implement them. All right. Okay, a couple questions I want you to think about. First, oh yeah, not a couple questions, just one single question. I already answered the one, which is what thread should get unblocked. We're using FIFO ordering. So if you use a queue, just take the front one off. The other question I had is if there are no threads waiting on a condition variable, okay, so no one is waiting, and you call signal or broadcast, what's supposed to happen? Okay, I went over this in the video from last week about the chemical reaction problem, right? If that happens, well, nothing should happen, right? Nothing should be recorded. Signal just does nothing if no one's waiting. Okay, if another thread comes and waits, that thread still has to wait until someone else signals or broadcasts after the wait is called. Cool. All right. Otherwise, I think we're all mostly set. That's it for condition variables. And let's just look at the test cases. I think there was a question on Ed about these test cases. So I think I should just quickly give you an example of what this test case is saying. Okay. Let's look at this test case. Okay, so we create a mutex, and then we create a child. Okay, so think about what happens here, right? What does your ready queue look like at this state? Ready queue should be basically the child, while the currently running current. Right? Then you call m.lock. So if you call m.lock, then the parent acquires the lock, right? Because there's no one else locking it. So main child. Okay, so yeah, then you call yield. So the parent holds the lock, and then it calls yield. When yield happens, right? When yield happens, the current thread gets switched off, and then gets switched off, and schedule gets called. So because schedule gets called, the parent goes back in the ready queue, right? Then the child gets to run. So child becomes the current thread. So we're running this thread, and the child attempts to lock. But the thread that was passed in here, by the way, it's by reference because you can't copy mutexes. So that's why this is by reference. When you try to lock here, the thread, the mutex was already locked. So because of that, mutex was locked. So child thread gets blocked, and it gets moved to the waiting queue for M. Remember, the mutex has a thread queue of all the threads waiting for M. Well, here that thread gets moved onto that queue, and child is not on the ready queue, right? It's blocked. It's not ready to run. Then remember what happens, right? Then when the child gets blocked, then the scheduler decides, okay, well, now we can just run some other thread. So now here, if we run this again, now the ready queue, now the current becomes back to the parent, while the ready queue is now empty, right? The child was not added to the ready queue. So that's why we continue. Oops, maybe I should make it more clear. So this is what happens after this point. So the current becomes the parent. So the parent starts to run again. So parent starts to run again, and parent releases the lock. Remember what happens when the parent releases the lock, right? When the parent releases the lock, it has to go into the queue of the threads waiting for the lock, and it takes the first one out and it unblocks it. So what this does is the first thing in the queue, child, gets unblocked because the child was the only thing in the waiting queue for the lock. So now your ready queue looks like child and parent. Remember, when the child gets unblocked, it doesn't just immediately start running. It gets put back into the ready queue while the current still runs. Right. So then the parent then reacquires the lock, and then parent requires a lock. Yeah. And then the function continues. Okay. So yeah, so I sort of went through an example of what is happening. Just important that when the child tries to acquire the lock, but it is already locked, it gets put onto the lock's waiting queue. It does not get put onto the ready queue. When the mutex is unlocked, the parent is responsible for moving the first thread out of the waiting queue of the lock it just unlocked, and it moves it back into the ready queue, but the parent is still running. Okay, yeah, that's an example of that test case. Then the other test cases are pretty similar. You can walk through that logic again. Highly recommend that you all do that, just walking through this logic, because this is a good practice for like trace problems on the exam. Yeah, so similar problem here. We're just trying to, now you have multiple children each trying to lock each other. Then here's a test for the condition variables, calling signal. Yeah, maybe just go through this code and try to annotate what the state should look like, right? What should the current thread look like? What should the ready queue look like? What should the waiting queue for the lock or for the condition variable look like? Okay, it's great practice for the midterm. And it also, if you annotate it here, what you can do is you can then do some print statements. For example, here, I can do, okay, so you can try what you can do is you can try printing out the ready queue. Okay, so do a for loop, get the ready queue, try printing the ready queue out. Now you will get an issue, which is the ready queue is like private. So what I recommend that you do is you can temporarily make the public members, the private members of the thread class and the mutex class and the condition class, make them public temporarily so you can print them. And then you can go through your code and check whether the actual ready queue or the waiting queue of each lock and condition variable and the current thread, whether that matches what, when you went through and annotated it, it matches what you think it is. If it doesn't, then there's probably some bug in the code that you can try to fix. You can also use GDB as well. All right. Otherwise, I think that is mostly it. I think that's mostly it. Oh, yeah, just forgot to mention one last thing. Syntax-wise, right? If you want to call a static function from, if in your code you want to call a static function, for example, if you want to call current, then you can use the syntax, right? That's a static function, so you access it by giving the name of the class. But if on the other hand, you want to call a member function like schedule, then you would need to find some sort of thread, right? There's some thread that you can call schedule on. Okay, that's just the syntax for calling the functions from project 2. All right. Otherwise, I think we're mostly done. I've gone through the starter code and went through the logic of mutexes and condition variables. So thanks so much for watching this video. Once again, if you have any comments or feedback, you can comment on the ed post. You can also send me an email. My email is averywong@stanford.edu. So yeah, thanks so much for watching this video. I went through a lot of bonus C++ content in here. So if you want to learn extra C++ stuff, I used to teach 106L, and the videos are actually on my YouTube channel. So feel free to check it out. Subscribe, whatever the YouTubers do these days. Okay. All right. Yeah. Thanks for coming. I will see you not next week because there's no project assigned next week. They have a midterm. I'll see you 2 weeks from now when you do project 5, which is about memory mapping. Otherwise, good luck on project 4 and good luck on the midterm. Bye. See you in 2 weeks.